find the Taylor series expansion for ln x about 1. Okay, so we know that f of x is equal to ln x. So let's start finding our derivatives. So we put together the Taylor series expansion. So the 0th derivative is going to be simply ln x. And we will evaluate this at x equals 0. I'm sorry, x equals 1, which is ln 1, which is, of course, 0. And then we'll take the first derivative, which is 1 over x, evaluated at x equals 1, which is just 1. Then we have the second derivative, which equals a negative 1 over x squared, evaluated at x equals 1, which is a negative 1. Then the third derivative, I'm just going to go out 3, 4, 5, whatever, to a point where I can clearly see what's going on. This is going to be, and notice the way I'm going to write this derivative this time. This is negative 1 times a negative 2 over x cubed, evaluated at x equals 1, which is negative 1 times negative 2, which is a positive 2. And see, then my next derivative is negative 1 times negative 2 times negative 3 over x to the 4th, evaluated at x equals 1, which is negative 1 times negative 2 times negative 3, which is a negative 6. And let's go ahead and do just one more. So I think the pattern now is getting to be pretty obvious. The fifth derivative is going to be negative 1 times negative 2 times negative 3 times negative 4 divided by x to the 5th, evaluated at x equals 1, which is a negative 1 times negative 2 times negative 3 times negative 4, which is actually just 6 times negative 6 times negative 4, which is a positive 24. So I think that's enough. I can get the general idea what's going on here. So I'm going to take this and say, all right, ln x is approximately equal to, let's put these together, 0 times x minus 1 to the 0 over 0 factorial. Remember, I'm expanding about 1, and that's where that 1 came from right there. And then I have a positive 1, so it's going to be plus 1 times x minus 1 to the 1st over 1 factorial. Then my next constant is a negative 1, so this will be minus x minus 1 squared over 2 factorial. Now I have a positive 2, but when I write that positive 2, what I'm going to do is I'm going to write that as a negative 2 times x minus 1 cubed over 3 factorial. Now I've got this, well actually this should be a negative because it's a double negative, so I'm going to make that a minus 2. Now I have negative 6, so I'm going to make this, put the negative here. And this is going to be negative 2 times negative 3 times x minus 1 to the 4th over 4 factorial. Plus, what do I have here? I have a negative 1 times negative 2 times negative 3 times negative 4 times x minus 1 to the 5th over 5 factorial, and so forth, and etc. Now, I wrote all these out like this so you could see them, all these constants like this, because of what's going to end up happening to them. Because what I want to do is I want to figure out where this is going to simplify to. Well, this is just 0, so I'm going to ignore that. That's just 0. This is going to be nothing but x minus 1. I'll leave it to the first over 1 factorial, or just 1, because that's what 1 factorial is, minus x minus 2 squared over 2 factorial is just 2. So what I'm going to do now is, this is a double negative, so let's make it positive. See, the 2 is going to cancel that 3 factorial. So what I'm going to end up with is plus x minus 1 cubed over 3 minus, well, see, these double negatives here is a positive. I have 2 times 3. That's going to cancel that 4 factorial. So that's just going to give me x minus 1 to the 4th over 4 plus all these cancel. And this is all going to cancel with the 5 factorial to give me x minus 1 to the 5th over 5. And I'm sure you can figure out the next term is obviously going to be a negative x minus 1 to the 7th over 7, and so forth. So now I can see that this is the approximation for ln x, and if I go to infinity, it should be ln x. So let's take a look at that and see if we can actually come up with the infinite series. So I'm going to say that ln x is actually equal to the sum. N equals, I'm going to hold off on the n equals for a minute and see if I can't figure out the other pieces and then figure out where I need to start n from. I'm obviously going to have alternating, so it's going to be negative 1. And I don't know if it's the n or n plus 1, so let's just hold off on that for just a moment. And I'm going to have, see, x minus 1. X minus 1 raised to the what? Well, let me see. If I do this to the n, divide it by n. Now, when n equals 1, I need this constant to be positive, so this should be n plus 1. So I'm going to go n equals 1 to infinity. Now, if we put in a couple values, you'll see that actually works. Now, the obvious question is, where is this going to converge? For what values will this converge? And we will do what we always do. I'm going to take a look at, I'm going to rewrite this real quickly here. Ln x equals the sum n equals 1 to infinity, negative 1 to the n plus 1. This was x minus 1 to the n over n. So I need to take a look at the limit as n goes to infinity. Absolute value negative 1 to the n plus 1 times x minus 1 to the n plus 1 over n plus 1 times n over negative 1 to the n plus 1 times x minus 1 to the n. Well, these negatives, negative 1s, I'm going to get rid of. The absolute value takes care of that, so I don't really care what's going on there. So this is going to be equal to the limit as n goes to infinity of absolute value x minus 1 to the n plus 1 over x minus 1 to the n times n over n plus 1. Obviously, this is going to cancel, and this in the limit will go to 1. So what I end up with is the absolute value of x minus 1, which has to be less than 1. That would then imply that negative 1 has to be less than x minus 1, which has to be less than positive 1, which tells me that 0 has to be less than x, which is less than 2. So I know that my radius is 1. And right now I'm looking at an interval from 0 to 2. And what you really need to do is take a look at this at the endpoints and see if it converges at the endpoints. I'm going to leave that up to you to do. I'm not going to do that right now. But you really should look at these endpoints to see. Okay, so here's my Taylor series expansion about 1 for ln x. And like I said, you need to take a look at these endpoints to determine whether I have a half open or a closed interval or what's there. All right, so now let's take a look at a Maclaurin series for sine x. So I'm going to go through the exact same process. F of x, well, let's just go right to the 0th derivative. The 0th derivative of x is sine x. Evaluated at x equals 0 because it's a Maclaurin series. Well, that's going to be 0. The first derivative of x equals cosine of x, evaluated at x equals 0, which is 1. the second derivative of x equals a negative sine of x, evaluate x equals 0, which is 0. The third derivative of x equals negative cosine of x, evaluated at x equals 0, which is a negative 1. And I'm thinking I don't need to go any further because I can see what's going on. All of the even derivatives are going to be 0, so they're going to go away. And then what's happening on the odd derivatives is every other odd is going to end up being plus 1 negative and plus 1 negative. So I have this alternating situation going on. So for the Maclaurin series, I'm going to say sine of x is approximately equal to 0 times x to the 0 over 0 factorial. And obviously that first term is not even needed because I think you can see that that's simply going to go away. It's not that big of a deal. Plus x to the first over 1 factorial minus x cubed over 3 factorial. And the next term is going to be the next odd terms is plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial, and so forth. So if I'm going to write this as a series, I'm going to say, all right, sine x equals the sum, and I'm going to write this as negative 1 to the n, x to the, not the n, but if I look at this, I need the odds, so 2n plus 1. That guarantees it's always odd. Over the factorial, these are all odd factorials, so I need 2n plus 1 factorial. Now the question is, where am I going to start? I'm going to start at 0 or 1. Well, if n equals 0, I'm going to have x to the first, a positive x to the first over 1 factorial. That's that one. When n equals 1, I'm going to have x cubed over 3 factorial. And this is odd, so it's going to be negative. So that's good. I'm going to start at 0. There's my series. Now, what I also need to do is I need to consider where is this going to converge. So like usual, I'll take a look at the limit as n goes to infinity of absolute value, negative 1 to the n plus 1 times x to the 2 times n plus 1 over 2 times n plus 1 plus 1 factorial. Yeah, I kind of ran out of room here. Times 2n plus 1 factorial over negative 1 to the n times x to the 2n plus 1 and absolute value. Sorry about that. That kind of got messy in there. Okay, so this is going to be equal to the limit as n goes to infinity. Again, absolute values, those negative ones don't mean anything. I'm going to get rid of them. This is going to be absolute value of x to the 2n plus 2 over x to the 2n plus 1 times 2n plus 1 factorial over 2n plus 3 factorial. Oh, this is going to cancel to give me just x. And this is going to cancel to give me x plus 3 times x, or I'm sorry, 2n plus 3 times 2n plus 2. So what I'm looking at now is the limit as n goes to infinity of x over 2n plus 3 times 2n plus 2. And then limit that equals 0. Therefore, this series will converge for all x. So it doesn't matter what value of x I put in here. This infinite series will converge to sine x.